Hi everyone, I am Pravalika and my teammate Harika. We are doing a project on plant disease recognition and where we are comparing our CNN with the transfer learning models. Yeah, next. Yeah, coming to the problem overview, the main reason this matter for the project is plant disease can reduce the crop yield and early detection help the farmers take action sooner. So traditionally, this was done by the manual inspections, which was slow and also depend on a lot of expertise, and the opinion was often subjective. So our goal here is to use the deep learning, specifically as this is the images, we are going to use CNN to classify the leaf images into healthy powdery and rust. The key challenge is the the data set is a real world data set where we have images taken in the outdoors where the background is very clutter and the lightning variation. So the problem becomes more realistic and challenging for us to do. And coming to the problem statement is very straightforward. We need to build a robust image classifier that predicts one of the categories like healthy, powdery, or rust. When I say the robust, it means like the model need to generalize well on the unseen data, not just on the train or test data set. And because we choose the data set from the real data set where the background is also very greenery. So we aim to do the models which generalize well on the unseen data or like for the future predictions as well. Yeah. Coming to the related work. Yeah, we have done enough literature work on this project because most of our models or the pre-trained or the CNN models are directly influenced from this literature study because uh, early studies like Mohanty and the co-founders in 2016 showed CNNs can achieve like high accuracy on the data sets like Plant Village. But the Plant Village data set, when we take a look of over the data set, it has like very clean backgrounds and the consistent lighting and all. But other works like Sandia, Vic, and the co-founders and confirmed like CNNs were well under the clean settings, but when it come to the realistic challenges like real world data set, the research highlight the key issue like when they move to the control data set to the field images, generalization become like harder and the models trained from the scratch CNNs and the custom CNNs can start rely on the background noise, like capturing the background noise instead of the main disease or the main leaf. So the performance can obviously drop. So then we go for the other researchers like the two and the co-founders in 2019, where it is important because they show the transfer learning usually outperformance like baseline CNNs and the custom CNNs, where the data set is small. In our case, which is true because our data set is very small. So and to understand the choice of like pre-trained models later, we also refer like FuresNet and the VisionNet and uh, uh, the founders which publish these residual connections that help the deep networks train the model and make the model stable. And overall, our literature strongly support our like transfer learning or the baseline CNN models, like how to design our model and how to actually implement the model. All these ideas come from main background literature review itself. And let's have a look at the data set first before going to the models. Can you show the data? Yeah. Yeah, our data set is from the Kaggle and it's a open source data set, and the images are real world, real outdoor images. And these data set have a three class classification like healthy, powdery, and rust. And the total images in the data set is very small, like 1532, and it was already predefined with the try and validation and the test data set. And at the end, we get the test data set as 150 images, and across the train validation and test, the data set is very balanced, and that is one good thing from the data set. And coming to the images, the images are a very high resolution, having a very high resolution, like it goes up to 5184 and 3456, which obviously need a strong pre-processing and augmentation settings. So as we have a very small data set and we want to design a perfect model, so we need to go through the data analysis first and see and have a look at how the data is distributed and how the images and everything was having the resolution and all. So let's go to the exploratory data analysis and its results. Uh, when we perform the EDA, we understand the dataset quality and the visual characteristics. We first check the dataset quality and all images are readable and RGB images, and we confirm there is no corrupted files and there is no duplicates and all, because anyway we have a very small dataset. So if we have duplicates and again the count go down, and that's why we checked everything. Then we look the class balance and which is obviously and nearly balanced. And we also check the image characteristics. The images are like a bit high resolution and some having like very large size and some are like in the medium sizes. So for the deep learning models, we need to, set the resolutions and all as a pre-processing step. And we also look at the brightness and the color trends, like obviously as this is a plant recognition, the green is dominating all over as expected. And when we saw the images like from the training data set, we easily can see the rust images, we can easily identify because of the marks and all. But the powdery and the healthy images are like bit tricky, because the powdery images are like having like brighter tone and having like whitish coating, which makes the models get confused easily when compared to the rust one. And finally, what we observe from the EDA is like the rust images are like very much clear with the spots and everything. But when it come to healthy and powdery images, the images, the contrast and the shadows and everything was overlapping with each other. So let's see like how models can classify these and uh, whether they're going to classify it correctly or not. And before building the model, as we said, our from the data analysis we need the pre-processing and augmentation, obviously, mainly for the custom CNNs. For pre-processing, we resize the images to fixed input sizes, and we used like 128 by 128 for our custom CNN models, because it trains fast and gives the solid baseline quickly. And we also used like 224 and by 224 for models we wanted to fair comparison with the transfer learning, because the most pre-trained model architectures uh, are expecting the 224 by 224 size. So to have a fair comparison between the baseline CNN models and the transfer learning models, we also had a version of 224 resolution models. And also we normalized the pixel values before training. For augmentation, we applied it only on the training set, like random flips, a small rotation, zoom, and the brightness, contrast adjustments, and all. The goal here is to help the model generalize like under real world lighting conditions and orientation changes without changing the validation and the test distribution. We only applied all these changes to the trained data set so that it can generalize well on the unseen data later. Let's go for the baseline model. Yeah, coming to the baseline model, we want to do a very good baseline model, because as already the earlier study shows, the transfer learning may work better on the small data set. So we want to try equally spend equal time on the custom CNNs, whether it can perform good with a proper model designing techniques and all. So as a reference point, we started with the this baseline model. Later we can use the transfer learning techniques and all. And also it helped us to understand whether the data set contains like strong disease signals that can be learned from the scratch using this CNN model techniques. And also we want to see what model can do mistakes like in the classification, where it get confused or where it fall behind when compared to the pre-trained models. We want to see that. That is the reason where we going with the custom CNN models first. And coming to the architecture, the baseline CNN is straightforward architecture with the convolutional layers with the ReLU and max pooling to reduce the spatial size. Then the dense classifier with a dropout and L2 regularization to avoid the overfitting. And finally, a softmax layer for the three classes. And we trained using Adam and space categorical cross entropy because the labels are integer encoded. And we ran the baseline at two resolutions, as we said, like 128 by 128 and 224. And uh, the resolution increasing is not just to see like whether the resolution changing itself will improve the accuracy or not, but the other reason is to have fair comparison and also to see keeping the same model with the changing the pre-processing step whether it can improve the model accuracy or not. That is the main reason behind the two variants. And let's have a look at the baseline results. When you see the baseline results, the curves look like very converging, and it stand out the best baseline model we can do. Even though we tried the improved models later, the baseline, the test accuracies and everything, the losses and everything where we got in this baseline is very standard and the strong reference points for the transfer learning models. In the baseline models, we achieve like 94% accuracy on the test data and with a loss of 0.19 only. And the main, even if you see the 224 results, the baseline results, it was the model is very converging and the loss curves look very close, and there is no problem of overfitting at all in this baseline. So let's see like whether we in improved models whether we can achieve good accuracy or like with the different model techniques and improved model whether the model can generalize well or it can get the better accuracies than the baseline model. So after the baseline model, we designed and improved CNN mainly to address the two things, like one to reduce the uh, misclassification between the healthy and powdery classification, uh, and whether the improved models can learn the richer texture features, and uh, whether they can stabilize the training under the lightning versions or not. So we increase the network depth and we added a batch normalization. We also kept the regularization like dropout, and we also trained with the early stopping techniques to overfit. We have taken so much care on this overfitting techniques because, as we said, the data set is very small, and when we go with the deeper networks and more epochs, there is a high chance of overfitting. So in this improved version, we make sure the model is not overfitting at the first place, and uh, we try to increase the model generalization and the test accuracy. And let's see the results from the improved CNN model. The improved CNN model achieved like performance very comparable to the baseline, and 128 by 128 improved CNN model is very much and exact accuracies matching with the baseline results. So, but when we look at the curves either in both versions, the model is very converging and very stabilized. Even though we run for the long epochs, the model is generalizing well. So we can't say like improved version is not performed better than the baseline, but we can say it was very equally performed to the baseline. And even we tried many different improved versions from the baseline, but no other model can beat the baseline performance, like the test accuracy out of the 94. So where the improved model and baseline model have the same results so far, and even the 224 improved model also not able to outperform the baseline. So that's where we stop spending like too much of time on the improved versions and trying to generalize the model more and forcing the model to to classify the healthy versus powdery images, because when we try that the model is going to overfit, and we are not able to reach this the good accuracies where the improved and CNN baseline models have set as a 94. So that's why we moved to the transfer learning techniques. And let's see like whether the transfer learning techniques work better for our problem or not. I'll handle it to the sorry, I hand over it to the Harika to for the pre-trained models.
Yeah. Thank you, Pravalika. Hi, everyone. My name is Harika, and I will be taking over from here. Now that up till this point, we saw that CNN's trained from scratch worked reasonably well, but they did struggle because our data set is very small and the disease patterns are subtle between the healthy and poultry. So, to address this, we use transfer learning, where we start from models that are already trained on very large data sets like ImageNet, and then we use the pre-trained models. Then again, we fine tune them, and again trained them to see the results between just the pre-trained models and the fine-tuned models. We used a two-stage approach. First, we froze the pre-trained backbone and trained only the classification head. Then, in the second stage, we fine-tuned some of the deeper layers using very small learning rate. This will help the model adapt to plant disease patterns without overfitting. So we tested using three different models based on our literature survey to the related work. The models we chose are VGG16, ResNet 50, and EfficientNet B0. Let's go over each model briefly. Coming to VG16, it has a simple and uniform architecture that stacks convolution layers. It is very good at learning texture based features, which are important for our plant diseases. Coming to ResNet 50, it uses residual connections, which help a very deep networks train more reliably. These skip connections allow gradients to flow better during the training. And coming to the one final model we tried, efficient and B0, is more of a modern and parameter efficient model, and it balances depth, width, and resolution. And it that's why it is a good choice when data is limited and overfitting is a concern, which is the case with our data set as well. Coming to the very first model, which is efficient net BO. So for all of these models, we took the input size as 224 into 224. So coming to the pre-trained efficient net BO results, we do see that the convergence is fast and very stable validation curves. The model did achieve a very strong test accuracy without much overfitting, as we can see in the images. This shows that efficient nets pre-trained features transfer very well to our plant disease dataset, even without fine tuning, because this is just the pre-trained one. So in this image, we can see the fine-tuned results of efficient net BO. We fine-tuned by unfreezing only the last few layers and using a very small learning rate. Even though fine-tuning slightly did improve the training behavior, the final test accuracy remained the same as the pre-trained even after fine-tuning. So we can say that the frozen efficient model is almost gave almost same results as the pre-trained model. Next, we have VGG16 pre-trained model. It is already pre-trained on ImageNet dataset, and it has already learned visual features like edges, corners, textures, simple shapes, etc. For VGG16, we first used it as a frozen feature extractor. All convolution layers were kept frozen and only a new classification head was trained. We can see the results here of the pre-trained model. It since it has a strong texture based features, it performed very well for our data set. The model converged quickly, as we can see, and showed smoother validation curves compared to the scratch CNN. This confirmed that pre-trained features are very helpful when the data set size is very limited, which is true in our case. Next, let's see the fine-tuned VGG16. So after that, we fine-tuned VGG16 by unfreezing some of the deeper convolutional layers. We used a smaller learning rate to avoid large weight updates. Fine-tuning allowed the model to adapt better to the disease-specific textures and color variations in our leaves images. Now, coming to the results of the VGG16 fine-tuned model, we can see that improved test accuracy, we had to be careful to avoid overfitting. As we can see in the image, there are few jumps here and there in the accuracy and the loss. Um, but we did see an improvement in the accuracy. Now coming to one more model we tried, which is ResNet 50. This is the pre-trained model. It is also pre-trained on ImageNet dataset. And we also evaluated ResNet 50 using a frozen backbone setup. As ResNet uses residual connections, it handles deeper architectures more effectively than the standard and the custom CNNs we experimented before. So, coming to the results of the pre-trained model, even without fine tuning, ResNet actually showed very strong and stable performance, and it gave us best accuracy among the all the other CNNs, VGG, EfficientNet, etc. So we also tried to fine tune the ResNet, and again we ran the model. Uh, Here are the results of fine tuning the ResNet. So among all the other models, again we saw that this gave the best accuracy. Now, coming to the final results. So, overall, we did observe a very clear pattern in the results. CNNs trained from scratch achieved decent test accuracy. Like we can see here, it's 94%, 92%, and we have again 94%, 91%. But in contrast, using the transfer learning models helped our dataset very well as they converged faster and generalized better and also produced smoother validation curves. So, fine tuned VGG, we can see, gave us 98% accuracy, and we also see that fine tuned ResNet gave us 98% accuracy with only 6% test loss. Coming to the confusion matrix, we can see the comparison between baseline CNN and best fine-tuned model, and we can say that it was able to classify better between healthy and rusty. Over to Pravalika.
Yeah. And before we conclude the project, we want to share like what challenges we really face with the project throughout. The first thing is the validation data set is very small. We only have like very small set like 60 images for the validation curves, and it the curves in all the models like even in baseline and CNN models and even the pre-trained models, the curves look a bit noisy when come to the validation curves because of the small data set, and even the one or two misclassification lead to the big drop in the curves. So this was very challenging, and we want to rely only on the final test accuracy to judge the model. So that's why we took the test accuracy as a main uh, test metrics for this project. And overfitting is also a risk because as we have a very small data set, like overall data set, uh, there are very high chances of overfitting thing, because even in when we try to improve the CNNs, uh, that can easily going to overfit when we increase the epochs, or when we try to go with the deeper models, or when we try variations in the model, it is very easily overfitting the model. So it is one of the major challenge and limitation for us. And also one of the major thing in our data set is like healthy versus powdery is very genuinely hard, because even some images are like very ambiguous. Even for humans cannot even predict the label properly because of these lightning effects, and the similarities between the overlapping between these two classes is very tricky for the pre-trained models and even for the baseline models. That is where one place where most of the models failed or struggle to categorize these two labels. And coming to the conclusion, as a part of this project, we have learned many things, like from the pattern recognition point of view, that even though challenges with the data set or instability in the data set, like how can we better use the pre-trained models, like because when we dealing with the pre-trained models, the overfitting is a very common thing for given like very small data set. So we learn the techniques like how can we overcome these overfitting things, and how can we build the models, and how can we design the models based on the data set, based on the data analysis, and like based on the already related work what others have done in the same field, that help us a lot, like to design the model, or to build the baseline models, and like creating the improved models based on all the techniques we have found. And overall, to conclude, like even though the background we have like very background issues in the data set, and the custom cnnns have a strong baseline, we can clearly see like pre-trained and transfer learning models become like more reliable approach for this small data set. And because the pre-trained models bring such a strong representations and the generalized better, so for the future work, like we try to improve the robustness, like which comes from the data and the pre-processing steps, just for the bigger models, like collecting the more diverse samples, like expanding the validation, like using the segmentation to reduce the background influence, and testing the lighting variant models for the deployment and all. So we want to try this as a future work, and we want to conclude this as a project. And thank you for having a look at our project. Our project.